Hi everyone. So today for week 10, we are going to get into Earth's history. So we're actually going to talk about the history of the Earth from its formation to today. So that is quite a bit of time, many billion years. So we're going to split it up. You're not going to need to remember too many terms, too many names, but I will make sure you know the most important aspects. So this is not a biology or evolution class, so we're not going to get too much into it. So there are some really important parts that you will have to know about Earth's history. So we're going to just sort of outline the changes that our planet experienced during the first 2 billion years. In terms of geology, tectonics, and a little bit about life, because that's pretty important. And we'll talk about the different tectonic conditions and settings, and then just a little bit about life, including human life, because it's just a little interesting to know when humans began. So this is the slide that you're going to want to remember. So I will not ask any more detail than what is on this slide here. So our history of the Earth is split into eons. The eons are split into eras. The eras are split into periods, and the periods are split into epochs. So for this class, really you should know the names of the eons and the order. And then these 3 eras, which are within our most recent eon. So these 2 columns are what you're going to want to remember, their names and the order with which they came, and also the main important things that occurred in each one, which is what we're going to go over today. We're really not going to get into too much detail with the periods and the epochs. It's just too much to remember. We're really just doing an outline or an overview of the history of the Earth. Now, this is billions of years, so we can't fit everything, of course, into this lecture. So we're just going to be talking about really the most important things. So I'm going to be going through from the formation through today. So this whole PowerPoint is going to be sequential. So we're going to go through the different eons, the Hadean eon, the Archean eon, the Proterozoic, the Phanerozoic, and then within that eon we have the Paleozoic era, the Mesozoic era, and the Cenozoic era. So this is our current era. So I'm going to go through the main components, the main points that happened in each one. But other than what we cover in this PowerPoint, any further details are a little unnecessary for this class. So I think our textbook goes into more detail. So if you are following along in the textbook, just beware that you might be getting some extra info, which of course is no harm. But don't worry about remembering every single little thing that happened in the history of the Earth, because that would be way too much information. So currently, we are in the Phanerozoic eon, the Cenozoic era, as we talked about. That's these guys that we're going to be learning about. And then we are also, of course, in the most recent period, epoch, and age. So this is a chart that you will see today in your lab, I believe. Yeah. So this is the start of Earth is over here. Then it sort of goes like this, and then goes like this, and then goes like this to the most recent time period, which is here. Okay, so let's get into it. Let me get my laser. Here we go. So the first eon, our very first one, is the Hadean eon. So we're going to start there. So the Hadean eon covers the formation of the Earth through about 4 billion years ago. So remember that GA stands for, that means billion years ago. So from the formation of Earth through 4 billion years ago, we consider the Hadean eon. You can remember that because it's like Hades, if you've ever seen Hercules, the movie. Hades is the god of the underworld back in mythology, so everything was really, really, really hot and on fire in the Hadean eon. That's how I remember it. So Earth is about 4.5 billion years ago. So this is when the Earth formed to its full size, how it is now. It started to differentiate. If you remember, that means all of the heavy materials fell to the center. So we have our our heaviest materials in our core and the lightest materials in our crust. And we had the creation of the mantle during this time. So at about 4.53 billion years ago, we had our formation of our moon. So the moon was actually formed by another impact. So an impact of something else orbiting the sun smashed into the Earth, and a bunch of debris broke apart. So the thing that combined with us, that hit us, and part of the Earth itself actually blasted off into space. So all of that debris eventually coalesced into our moon. So all of that debris was orbiting around the Earth and eventually coalesced due to our gravity into the moon. So our moon was formed pretty soon after the formation of the Earth. And in this time, we also had a solidification of the surface of the Earth. So the surface of the Earth actually started to solidify into rock. It was all very ultramafic, but we did have solidification of our surface, so we weren't completely molten. The atmosphere at this time was very deadly. Nothing was alive. Really the only gases in our atmosphere were caused from volcanic outgassing. So all of the gases that are put out by volcanoes, which are pretty deadly, that's all we had in our atmosphere was from volcanic eruptions. That's actually where our atmosphere came from. And we had very common meteorites hitting the surface of the Earth because so much in our solar system was still forming. There was so much debris still in space. A lot of those meteorites were getting pulled in because Earth is so large and has such a strong gravitational force. So during this time period, we did have liquid water start to condense. So from the gases in our atmosphere that were released from these volcanoes, we did actually have liquid water begin to condense and fall and fill in the deepest parts of the surface of the Earth. So that is sort of the beginning of our oceans. So in the Hadean Eon, it goes up to 4 billion years ago. Earth was coalescing, all of those heavier elements sinking to the surface. We had water, we had the moon. Oh, and also our magnetic field was forming and solidifying and becoming similar to how we know it today in this eon. So the next one we have from 4 billion years ago to about 2.5 billion years ago. So this is where the crust actually cooled to start forming lithosphere that stayed. So a lot of the ultramafic rock that formed on the surface in the very beginning of Earth's history ended up sinking back down and liquefying and reforming in our mantle. So it didn't stick around on the surface. So the surface in the Hadean Eon, yes, it was solidifying, but it wasn't staying around because the mantle layer was too hot. There was still a lot of motion. So a couple billion years later, we actually had our lithosphere form and stay on our surface. So this is where we say our rock record begins, because at this point we had lithosphere forming that stayed lithosphere and actually stayed crust. So we had about 85% of our modern continental crust present by the end of the Archean Eon. So 85% of the continental crust that we have today had already formed at this point, which means plate tectonics was already occurring. So plate tectonics began, my favorite topic, began around this point in Earth's history. So this is looking at continental crust area, present continental crust area with time. So most of our continental crust formed in this eon. The next eon is really where we had up to 99% of our continental crust forming. But the majority of it formed during this time. When things were cooling, the crust was actually cooling enough to stay around. So what was happening is the crust didn't cool into continents. The crust cooled in very small sections. So tiny little areas of crust began to cool. We had some felsic blocks. So here are thicker, less dense felsic continental crust versus this dark gray is trying to show the denser oceanic crust. So this would be the mafic rock. Our felsic crust we know is not buoyant enough to subduct. So it's going to always stay at the surface. So what happened during this time is we had a lot of mini subduction zones. We had teeny tiny little tectonic plates and they were all colliding together. So you'll notice that with this subduction, these two are moving towards each other. This is a convergent boundary. So what happens is this block C here is actually going to move and combine with block B. The same thing's going to happen with this volcano and block E. So eventually, this is sort of time period 1, time period 2, all of this land is eventually going to combine together to create something larger. So when our first felsic blocks of land started forming in this period, they formed in really small regions that were all then combined into what we call protocontinents. So the first sort of continents were formed by the collision of all of these smaller areas of crust. So this forms the protocontinents that would eventually become the continents that we know today. So we not only did we have plate tectonic action, but there's also a lot going on in our atmosphere during this time period. So if you remember in the Hadean eon, we had a very deadly atmosphere. But what happened is the H2O, the water vapor, could condense, started to rain and fill up our oceans. So during this time, our oceans were accumulating water. We had a lot of liquid water on our surface, and that liquid water was actually able to dissolve carbon dioxide, similarly as it does today, from our atmosphere. So the oceans are actually what removed the deadly amounts of carbon dioxide from our atmosphere, allowing life to begin. So the oceans dissolved most of the atmospheric carbon dioxide, leaving behind nitrogen, which is what most of our atmosphere is now, and life was able to begin. So life started in our oceans about 3.8 billion years ago. We think we've seen from sedimentary rocks. So we've seen the chemical signature of life, but the very first fossilized cells have not, they were dated to be 3.5 billion years ago. The agreed upon sort of by everyone date of life beginning is actually 3.2 billion years ago because we have undisputed fossil forms. So fact, we absolutely know there was life by 3.2 billion years ago. These two we're still looking for more information. I mean, it's pretty certain, but in terms of our scientific process, these two have not been accepted by everywhere and everyone. However, we do have evidence of life back to 3.8 billion years ago in our oceans. So stratomolites are layers of sediment. This is what we actually look at. That sediment sticks to microbes or very, very tiny forms of life. so that life actually ends up trapped in our layers of rock. So we can actually look back into these layers of rock. We can use our isotopic dating, which we learned about using radioactivity and half-life, to determine exactly how old these layers of rock with the signature of microbes are. So life began at what we call the black smokers, or the hot water vents in the ocean. So this would be somewhere that we have heat from the inside of the earth escaping. So like a divergent boundary or mid-ocean ridge is going to have plenty of black smokers, which is the area where that heat escapes. So there was a lot of heat and a lot of nutrients coming out of these areas, out of this hot water vent, and that is where life was actually able to begin. So in this era, we have our first oceans, we have plenty of tectonic activity, and our continents, well, not our current continents, but our very first continents were formed. And we also had bacteria forming. That's our first life in our oceans. So at this point, you should be able to see that the answer to this is all of the above. So all of these things happened in this eon. So if we move on past our Archean eon to the Proterozoic, this is from 2.5 billion years ago through 541 million years ago. So this is a very, 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 very long eon. And this is actually named after the word for first life. So that's because we did not have the evidence to prove that life begins actually in the Archean eon when these times were named. So we originally thought that our first life was in the Proterozoic eon, and that's why it was named the Proterozoic eon. However, we have since discovered that life actually began much earlier, about 1 billion years earlier than we thought. So don't let those names confuse you. The Proterozoic eon is definitely where we saw a boom of life, but our first life was actually found previously. So in this time period, we have our continental collision is still continuing. At this point, we don't have as many teeny tiny pieces of crust. They are combining into larger and larger plates, the way that we have now. And this is when we had the Earth transitioning really into something similar to what we have today. So this eon is where there were a lot of changes that make the Earth look much more familiar to what we are used to today. So by this point, like I showed on that graph earlier, 99% of our continental crust had formed. So 99% of the continental crust that we have now had already formed by this time. New crust forms at really, really slow rates, but we did still have volcanic arcs combining and colliding into our continents, adding land mass. So you might hear the word craton when you're thinking of continents and proto-continents way back when. Cratons are what we call stable continental blocks. So when those small pieces of crust continued to combine into these larger bits of pre-continent, they were called cratons. So as you can see, these here on this image are actually dated. So they're dated by time period. So you can see when all of the mass was added to each craton, excuse me. So you'll see that our oldest is actually what we call the Canadian Shield. Everything else was added to that over time. So here's another figure that shows you in a little bit more detail when the land of the continent of North America was actually added. So everything in pink is the most recent. The oldest things are actually inside this craton. So all of this was formed either in the Proterozoic or before. And it was formed again by the accumulation of different smaller bits of land. So the smaller bit of felsic material combined due to different tectonic forces, pushing them towards this craton, allowing this landmass to grow and grow and grow. So it became one mass that actually sort of is continuing to grow even now. So our first supercontinent was formed in this time period. So you may have heard of Pangaea. So there were actually a few supercontinents before Pangaea. So about 1 billion years ago, we had Rodinia. So continental collisions, at this point, we have large continents. We don't have any tiny pieces of felsic crust left. They have all combined into these larger continents. And about 1 billion years ago, we had Rodinia, which looked something like this. And it actually rifted apart about 700 million years ago. So it formed into a large supercontinent and then drifted apart again. So plate tectonics brought everything together and then pushed everything apart, just like it's doing now. So about 700 million years ago, Rodinia split up and created, after another 100 million years, we had our second supercontinent, Pangaea. It didn't survive very long because this was still a period of really high tectonic activity. But it took about 100 million years to go from our first supercontinent to our second. And this second one did break up pretty quickly. So it didn't survive as a protocontinent very long. Plate tectonics then separated them again. So you'll see in these figures, these are from our textbook, they actually label the land masses as we know of them today. So this would be West Africa. You can sort of see the outline of Africa here. This would be North America, Hudson Bay. This is Greenland. This is Central America, Mexico-ish. This is Antarctica. So it's kind of cool the way that they show us exactly how the land masses moved through time. So after that time period, we had oxygen in our atmosphere increase greatly. So there was a boom of algae in our oceans. So life in our oceans, single cellular life in our oceans, I should say, was thriving. So this led to what we call the Great Oxygenation. Excuse me, the Great Oxygenation event. So this is when we had a huge amount of oxygen entering our atmosphere. So this allowed for significant iron oxide to form. So we had a lot of iron on our surface, and that iron was rusted, essentially. It was oxidized by the mass amount of oxygen in our atmosphere. So in our rock samples, in our sediment cores, we can see very, very clear lines of what we call banded iron formations, from where we have very clear red iron deposits. And we know that this very, very clear, very oxidized red iron is actually from this time period where we had a huge amount of oxygen in our atmosphere, allowing for this massive amount of oxidation of the iron on our surface. So this is one of the very clear keys to knowing what time period you're looking at, is if you see these banded iron formations, you know you're probably looking at this time period where we had that large amount of oxygen in our atmosphere. So the oxygen affected much more than just the iron on the surface. Of course, it definitely affected the life on Earth. So there was a huge jump, not only in the single cellular life in the ocean, which did thrive. We also had a large jump in the complexity of the life on Earth. So with this oxygen, this increased oxygen, a lot more life was actually able to form and grow and evolve. So we had the first worms and jellyfish, things that were soft-bodied, so we didn't have shells quite yet, but the first multicellular life So the first multicellular life was formed because of this increased oxygen in our atmosphere. So this was all in this Proterozoic eon. So after we had this fabulous boom of life, we have multicellular life thriving, we had what we call the snowball Earth. So our entire Earth was actually covered in glaciers. Our oceans were frozen. Everything on Earth froze. That is why we call it the snowball Earth. So there's a lot of evidence of that in terms of rock layers that have evidence of glacial activity. So a boulder this large, you can see compared to these two people, can only be moved by ice. There's no water force that could move boulders like this all over the world other than ice. So we know that glaciers were present because this boulder had to be moved in order for it to be an inclusion. We know that this boulder existed before this other rock. So this boulder came from somewhere and was placed as this secondary layer was being formed. So there's evidence of this snowball Earth all over the globe, which is very, very, very cool. So it's after this boom in life, we have our multicellular life thriving, and then the whole Earth freezes. So what happens? How did we thaw? We know now we're not covered in ice. We have some, but not everything. It's actually very similar to what's happening now. Because of this freezing, we actually had an increase of CO2 in our atmosphere. So the ocean was no longer removing CO2 from the atmosphere because the ocean was frozen. So what that did was it increased the greenhouse effect in our atmosphere. So CO2 is a really big greenhouse gas. It actually traps heat in our atmosphere, which allows the Earth to warm. So the fact that our oceans were frozen actually allowed for the oceans to thaw. Because that CO2 built up, our greenhouse effect got stronger, and more heat was trapped, so things began to thaw. So this killed a lot of the life on Earth, but not everything. So we think that life was able to survive only near those black smokers or some sort of hot spring where we had geothermal heat rising from the mantle, the center of the Earth area, out towards the surface. So after this thaw is where we had a really huge boom in life on Earth that we call the Cambrian explosion. So before this snowball Earth, we had multicellular life living, but they were not, they didn't have shells yet. After this snowball Earth thawed, that's when we had a really big boom in our life and our diversity of life on Earth. So here we had our snowball Earth in the Proterozoic eon. Multicellular life was able to form, and we had ozone stabilization, but we are not taking an atmosphere class, so we're not going to talk too much about that. So this leads us up to 540 million years ago. 541 million years ago. This is a really nice textbook from, a really nice figure from the textbook if you want to look at these figures. I found these cartoons, which I really like. They're pretty simple. These are from the book, which have quite a bit more information, and I think they're really well done. So if you want to use these for studying, I think this is a good snapshot of everything. So you guys can go back and answer these questions that I have throughout when you're studying. I think if we were doing this in class, I would have asked this to the class. But since we are online and you can't answer me in real time, I still wanted to show you the questions so you can study. So the next eon started 541 million years ago and is our current eon. So all the way up to present, we have the Phanerozoic eon. So in this time period, climate is warming, so we're warming out of that snowball Earth. Our continents are still drifting and life evolves drastically and very much diversifies. So in this eon, we break it into eras. So these are the 3 eras that you're going to want to know. There's a lot that happened in them, which is why we're separating for this class. Instead of lumping everything into the Phanerozoic, we're going to separate into these 3 eons. So the first being the Paleozoic, and then the Mesozoic, and then our current eon, which is the Cenozoic era. So in the beginning, we had the rifting of that sort of second supercontinent, Pannotia, and that pulls the continents on Earth into 4 pieces. So it's no longer supercontinents, it's really more like smaller continents, things that we have now, or what we call continental fragments, because they still are not the same as our current continents. So in the Paleozoic era, so we are here, the first era within this most recent eon is when we had shells forming. So shells, vertebrates, and land plants. So there's still plenty of life in the ocean, small life, nothing too big, but this is the first time that we have shells and also land plants. So life is creeping out of the oceans and out onto the land. So land plants, we don't quite have organisms on, animals or mammals or vertebrates on land, but we do have plants. So during this time, so sort of the end of the Proterozoic eon into the start of the Phanerozoic eon, so at the start of the Paleozoic era, is when we had the Cambrian explosion. So this explosion is when we had a huge amount of diversification of the life on Earth. So it took millions of years, but this is where we had organisms growing, food chains beginning, a massive amount of life started to form during this time period. Then there was a mass extinction caused by glaciation. Once that glaciation warmed up again, the climate was able to be stable enough for a long amount of time that we had another big boom in life. So the ocean was actually able to diversify and evolve quite a bit. And on land, we started to see plants that had roots, plants that had seeds, and also plants that grew wood. So these plants were able to grow larger and survive for longer. So it wasn't something just like a simple grass or a weed. Larger things with root systems that could keep them in place and seeds which could keep them growing over time actually allowed for plants to survive for much longer. And during this period, we had our first animals actually crawl on land and breathe with lungs. So this Paleozoic era is when we had the first land animal breathing with lungs, so not relying on the ocean for life. So in the Paleozoic era is where we had Pangea forming. So all the continental collisions ripped apart Pannotia and began to form Pangea, which is the most recent supercontinent. This is also when the Appalachian Mountains were formed. So the Appalachian Mountains are the mountains on the east coast of the U.S. that run north to south, sort of like the Rockies. We've talked about them a couple times in class. They were actually at one point larger than the Himalayas, taller, I should say, than the Himalayas, and have since been eroded because this was between 541 and 252 million years ago that the Appalachian Mountains formed. So there has been a significant amount of time for these guys to erode away, which is why the mountains aren't, they're absolutely beautiful, but they aren't as impressive as the Himalayas now. So the interior of the U.S. at this time actually looked something like the Bahamas. It was very warm. It was humid. There was an ocean in the center of the United States. And there were giant insects. So amphibians and reptiles really diversified and exploded on the earth. And this is a picture here to scale of an average dragonfly at this time. So note, of course, there were no humans. But if we were to put the average dragonfly size compared to a human, this is what it would look like. Terrifying, terrifying size of the bugs that lived at this time. Imagine a dragonfly with the wingspan almost as large as your own wingspan. That is one of the worst things I can think of right now. So, good for me personally, because that would be scary. There was a huge mass extinction. So Earth has gone through a lot of extinctions. The Permian extinction happened in the Paleozoic era, and that removed about 95% of our marine species. So this one was either due to volcanic activity or a meteorite impact. We really aren't sure yet. There's not a huge amount of data or evidence for this, but it had to be one or the other in order for the sunlight from the sun to be blocked by something in our atmosphere. So this extinction was caused either by volcanic activity or a meteorite impact. We really don't know. So the Paleozoic era, we had our Cambrian explosion, life diversifying. We had invertebrates, so finally we have shells, we have fish with bones, and land plants. Then we have things moving on land that are breathing with lungs, gigantic bugs, and then a very large extinction at the end of the Paleozoic era. And here again is the version from the textbook. So my question for you all would be, during which period did this guy, the Tyrannosaurus Rex, live? Take a second, think about it. Which period do you think that the Tyrannosaurus Rex lived? So hopefully you are all thinking, oh, Jurassic, because I've seen Jurassic Park the movie. Well, it turns out Jurassic Park led you wrong. So yes, it's true that the Tyrannosaurus Rex did live in the Mesozoic era, which is what we're about to talk about. However, Tyrannosaurus Rex did not actually live in the Jurassic period. They lived in the Cretaceous period. So the movie, I guess they thought Jurassic Park sounded better than Cretaceous Park. The dinosaurs, Tyrannosaurus Rex, actually did not live in the Jurassic period. They lived in the Cretaceous period, but they did have the era correct. So for our class, since we're really only thinking about the era, we do know that Tyrannosaurus Rexes did live in the Mesozoic era. So Mesozoic being from 252 to about 66 million years ago, this is where we had the explosion of dinosaurs. So this was the age of dinosaurs, and also the first time that we had things with legs beneath them. So the way that dinosaurs and us walk with legs beneath our bodies instead of out to the side like a lizard. This is the first time that we had legs on Earth that were actually beneath the body of the being. And this is the first sign of mammals. So in the Mesozoic era is where we had the first appearance of mammals. So here is a picture of what land looked like at this time. We have a subduction zone here. So this is a convergent boundary. So this plate subducting underneath this plate. We have a subduction zone here as well, convergent boundaries. So this here subducting underneath this here. And here, I hope that you notice, this is South America, this is North America, here's Florida, California would be over here. Well, actually, California would be over here. This is Africa. So this here is our Atlantic Ocean. So this is our mid-ocean ridge. So during this time period is where our mid-ocean ridge actually started forming and started splitting apart Pangaea and forming our Atlantic Ocean. So in the Mesozoic era is where we had Pangaea separating. So our mid-ocean ridge formed, and at this point India is getting ready to crash into Asia, but it hasn't yet. So we're still separating in between or on either side of the Atlantic Ocean. We're separating along that mid-ocean ridge, which we are still doing today. So in the Mesozoic era, we had sea levels were very, very high. So most continents actually were flooded. So this is something that you all drew out the week before spring break. Remember there was that shallow ocean in the middle of the US? This is it. This is the shallow ocean in the middle of the US. And there were a couple of reasons for the really high sea level. One being it was very warm, so there wasn't ice on Earth, because there was unusually high volcanic activity. So there was quite a bit of volcanic activity going on. We had a lot of warming in the atmosphere from that. We also had very high rates of seafloor spreading. So our seafloor spreading at our mid-ocean ridges was about 3 times faster than it is today. So the oceans were growing 3 times faster. What this meant is there was a lot of crust being formed. So there was a lot of new oceanic crust on either side of our mid-ocean ridge, and it didn't have as much time to cool before it was pushed further out to the side. So we had a lot of new, fresh crust forming, and that new crust was warm and also thicker because the crust, remember, condenses as it cools. So when it was thicker, it was a little expanded, which also displaces even more ocean water. So we had a warm atmosphere with no ice, and then we also had thicker crust, which allowed for even further displacement of water. So we had a really, really flooded bit of land. This is what the world would have looked like in the Mesozoic era. So we have what we know now as North America. Europe, Asia, India has not yet crashed into Asia. We know that that's coming. And Australia and Antarctica were still connected. But you'll notice there's no ice on Earth. So Antarctica is green. Up here in the poles, you don't see any ice because at this time there was no ice on Earth. You'll also notice that the continental crust is outlined in the light blue on this picture because it is not as dense. And it will be, the ocean would not be as deep in that area. So we know that the continental crust is still there. Even though this is underwater, it's still continental crust. Even though we have ocean flooding into South America, we know that this is outlined by continental crust. So there was a giant extinction, the one you're probably all very familiar with, in the Mesozoic era that ended our age of dinosaurs. There was a 13-kilometer wide meteorite that hit Earth and created a giant crater in what we now call the Gulf of Mexico. It created tsunami waves that were 2 kilometers high. That is so difficult to think about because it is huge. Tsunami waves that were 2 kilometers high when these dinosaurs went extinct. It also set almost everything on Earth on fire. This meteorite blasted so much debris up into our atmosphere, so the impact was so strong that there was so much debris and sediment and dirt and rock that actually blasted into our atmosphere that it blocked all of the sunlight coming to Earth. So the sky actually turned dark because this meteorite impact blasted so much debris up into space, up into our atmosphere. So this actually shut off photosynthesis on Earth for some time. So this extinction, we do have evidence of. The other one we talked about, we don't really have the evidence to say. This one we know for sure. The analysis of the rock in this area has showed that there was meteorite impact because of the chemical makeup of the rock there. There had to be something from space, from our meteorites that came and deposited the really abundant amounts of specifically meteorite chemicals, meteorite elements, which we don't see so much on Earth. And then we also see an evidence of that shutdown of our photosynthesis, where we know that sunlight was shut off to Earth, because there's actually a layer of clay, or one of our beds of sedimentary rock has no plankton in it. So there's no life going on in the ocean because there's no plankton. So that plankton was actually shut off or turned off, or they all died. They were not producing during this time. So that's the two key pieces of evidence that we know a meteorite did strike, and we know where it struck, which is what we call now the Gulf of Mexico. So here was that gigantic meteorite impact. So this is the Mesozoic era. We had Pangea, we had the age of the dinosaurs, and mammals started forming. And then we had our extinction. So in the Cenozoic era, which is our current era, so this started 66 million years ago through present. So this is our era currently that we are in. This is really the final stages of Pangea's breakup, and the surface of the Earth begins to look exactly as it looks right now. So India during this time did collide with Asia, creating those Himalayas here. We also had the continuing spreading of the mid-ocean ridge in the Atlantic, pushing the continents away to how they are now. And also the Ring of Fire was forming and very active in our Pacific Ocean. So all of these subduction zones that we've talked about many times in class were subducting. So tectonic activity in this time period is very, very, very similar to exactly as it is today. So during this time, climate cooled and glaciers appeared on Earth. So not quite like the snowball Earth where the entire Earth was covered, but it was cooler than it is today. So in the past million years, we've had glaciers the past 2 million years, we've had glaciers covering North America many, many times. But the last time that we had glaciers in the United States was between 110 and about 12,000 years ago. So we actually had that, we call that the last glacial maximum. So from 110,000 to 12,000 years ago, we had glaciers extending all the way down into the United States. So the ice sheet that we currently have on Greenland covered all of Canada, and then some of the northern US and all of New England. So that was called the Laurentide ice sheet, actually extended all the way down into the United States. So not quite into California, but we did have glaciers in our mountains in California because it was cold enough. So about 11,000 years ago, climate started to warm again, and we entered into what we call now the current interglacial. So in between times of maximum glaciation, where we have the maximum amount of glaciers on Earth, we call that an interglacial. So currently we are in an interglacial. So after the meteorite impact, the big one in the Gulf of Mexico, plant life recovered rather quickly. Grasses really thrived. They grew and they spread. And also mammals. So mammals did quite well when we began the age of mammals. So the Cenozoic era is when the age of mammals began. Mammals thrived. Dinosaurs did not. So dinosaurs, of course, were extinct after that meteorite impact. We no longer have dinosaurs. But in the Cenozoic era is when mammals started to take over. So about 4 million years ago is where we had the first human-like primate. The first member of what we call our human genus, the Homo genus, was 2.4 million years ago. And then the first time that our human-like ancestors stood up, so actually stood up and used their hands for making weapons and axes and things. So they were probably using obsidian or slate, something that's easy to shape, was about 1.6 million years ago. So it wasn't until 1.6 million years ago that ancient humans actually were standing up the way that we do now. But then a lot of time passed, and we didn't really have what we would call modern people until about 200,000 years ago. So 200,000 years ago, we did have modern people living in something similar to our modern civilization. But it we had, I think, 3 major species of humans. So similar to us, there were actually 3 species of humans to begin with. 2 of them died out, and by 25,000 years ago, Homo sapiens, so what we are now, were the only human species actually left on Earth. So our species, Homo sapiens, were the only ones left on Earth by about 25,000 years ago. So this is the Cenozoic era, so it started with the extinction of the dinosaurs, which allowed for the age of the mammals. So mammals thrived, mammals really expanded and diversified, and we have more of our modern Earth. So most land was covered by grass, and then we have the evolution of human beings begin at the end of the Cenozoic era up until now, where we are living happily taking geology online. So here's a review. We have our important eons, first the Hadean eon, and then the Archean eon, and then the Proterozoic eon, and then our current Phanerozoic eon, which includes the Paleozoic, Mesozoic, and Cenozoic eras. So those are a lot of confusing names, so that's why I put it all on this one slide. This is the same slide that I showed at the very beginning of the PowerPoint, because these are the names that you should remember. So don't worry about remembering any further detail than this. Even the specific times you don't need to remember as much, but you should remember these names and the order with which they come. So I have a video that I want to show that helps think about the length of time that we just covered in this short PowerPoint in my, 46 slides. So I have a video that I will show. It's about 3 minutes long, but it's pretty good, and it helps you get a sense of how long the Earth has existed and how little time we have actually been on Earth. So let's watch this. The link is there, of course, in the PowerPoint if you want to come back to it and watch it on your own. So we're already in the state of Pennsylvania before plants even start to grow on land. So that's the big meteorite that hit the Gulf. And here we have the age of mammals, occurring only 32 miles from our destination on this scale. So here we have people. We're already in New York. Look how close we are to Manhattan. This is Manhattan here. So we're 1 mile away. compared to our whole entire trek from California to to New York before we have humans evolving. Very, very, very close before we begin recorded human history. So that whole entire trek from the west coast all the way to the east coast, that whole distance of land, if we scale it to the history of the Earth, our recorded history, which began 5,500 years ago, would only take up 15.7 feet. So the concept of this many billions of years of the Earth's history can be really, really hard to wrap your mind around because it's just such a massive amount of time. So I hope that that video helps at least a little bit with scaling